Hello, welcome to today's video and potentially even welcome to this channel because I'm aware today's topic is something that's covered fairly near the beginning of A-level for most people, and therefore this might be your first experience of the channel, so in which case, welcome, good to see you here. Okay, so today's topic, we're going to be looking at index laws, and more specifically we're going to be doing a recap of them because they are in theory something that's been covered at GCSE, and we're going to be looking at the more advanced uses for them in terms of A-level questions, why are these things useful, all that sort of stuff. So without further ado, let's get kicked off. And the first thing we need to recap is, what are the index laws? So these are just basically rules that allow you to simplify things to do with powers, because that's what indices or index singular is. So let's take a look at them. The first one is if you have something with a base of whatever, x, to a power, and then you multiply it by something with the same base to a different power, what you've got to do is you've simply just got to add the powers together. So that's what you get in that case, combining the two powers in that way. If you're doing dividing, well, dividing is the opposite of multiplying. So if we have an x to the power of a divided by an x to the power of b, as we added the powers when we were multiplying, therefore when we're dividing we'll do the opposite and we shall take them away or subtract them. Nice. Third one is what happens if we have something to the power of something and then we take that to another power. Well, all you've got to remember is you've got to multiply those two powers together, and therefore you can simplify that way. However, there is actually a fourth index law that actually gets neglected a lot of the time, and it's how indices work with brackets. So, for instance, if you have a number multiplied by another number, or with algebra like I'm doing here, a times by b, and then you take both those things inside brackets to another power, then what that is going to do is it's going to allow you to apply that power to the individual things. Now, it's worth noting this is not to be confused with situations like this, because that is something where you can't just apply the powers to individual things. And the reason for that, well, the logic behind it, is simply that adding and powers are very different operations, and so they don't interact in a very particularly nice way. But if you think about this example above, well, you're doing multiplying and then doing powers. And the thing is, powers are just a quick way of doing lots of multiplying. So because those two operations are quite strongly linked, that is why they interact in a nice way. So something to be aware of in maths in general, and you'll see this across a lot of the videos. There's often a logic behind a lot of the things we do. And so, always try to remember why it works, because that can help make it easier to remember stuff. So these are the laws, these are the things you're allowed to use, but what sort of questions are you going to get? Well, the first thing to point out is that you're not going to be getting a question like you're used to at GCSE, where it's just simply things that are just like, the whole question is like simplify x squared times by x cubed. Because of course, yes, of course, you can use index laws in that situation, and it would be x to the power of 2 plus 3, so x to the power of 5. You're not going to get a question that's just that, because of the fact that's already been tested at GCSE. So instead, what you'll end up having to do is you end up having to use these index laws just to help you simplify as part of often doing other things in bigger questions. They're just basically tools to help us manipulate algebra into a way that makes it useful for us. So for instance, one sort of example we could have is something like this. The question will probably not even be simplify this, but we'll need to simplify this as part of doing another question, whether that's solving an equation or something else, I don't know. So first step is to realize also, we also have numbers, coefficients involved. And another helpful thing sometimes is to separate out the numbers from the algebra when you're doing that. So the first thing is we need to multiply out the brackets. That means we're going to be doing this thing times by this thing. So that means we'll have a 4x to the half times by a 6x squared. And then separately, we're going to be doing the plus 3 times by the 4x to the power of a half. So 4x to the power of a half times by 3. We could write this in a couple of different ways, so I'm going to write it with a multiply symbol there. But yeah, there's more efficient ways I could have written that. Okay, then we can actually start to simplify these two things. As I said, separating out the numbers from the algebra. The reason this works is because we've got 4 times by x to the power of a half, and then we're multiplying that by 6x squared. Now, because everything in this little bit of algebra that we're looking at is to do with multiplying, that allows us to then start focusing on different things in different orders, because multiplying doesn't matter what order you do it in. So we're going to do the 4 times by the 6 first, which will get us 24. And then separately, we're going to do the x to the power of a half times by the x squared. And we know from our index law from before, that means we're going to add the powers. And then over there for the right-hand part, the right-hand term, we've got 4x to the half times by 3. Well, again, separating out the numbers, that's 4 times by 3, which is 12. And by the way, we're adding all this stuff on. And then the x to the power of half, well, that doesn't have any other algebra to multiply by. So therefore, it's just got to stay as it is. The last step would be to simplify what we have now written fully, which is to realize in the power of the first thing we've got a half plus 2, and if you do some fraction adding, you could make a common denominator, all that stuff if you want to, or type into the calculator. Either way, you're going to get 24x to the power of 5 over 2, plus then the other thing we haven't changed, 12x to the half. Worth pointing out in pure maths, although you could write 5 over 2 as 2.5 in the power, generally in pure maths we prefer improper fractions, or top-heavy fractions as sometimes called, just because they're more useful for doing things like multiplying and stuff like that. So that's the way we'll leave it. Also, unlike decimals, you can often leave things in exact form if you keep it as a fraction. Okay, another example, slightly more complicated, uses a few more skills. Here's the example we got here. Now, lots of things are going on here. We've obviously got 2 pairs of brackets being multiplied by each other, but we also have that power of 2 there. And by the laws of BIDMAS, BOBMAS, PEMDAS, whatever you learnt it as, basically the rule that decides the order of operations, that power of 2 has to happen before anything else. So this is going to make use of that index law we talked about earlier, which is that if we have a b to the power of n, it's a to the power of n, b to the power of n, and therefore we're going to apply that power of 2 to both the 9 and the 4. So that means we're going to say it's 9 squared, and then we're going to have x to the power of 4 all squared. And then because we haven't done anything to the other bit yet, we just rewrite it as is. Okay. Then we can simplify that further, because 9 squared can be written as 81, and then the x to the power of 4, using the index law we looked at in the previous slide, we're going to multiply the powers together in that scenario. So 4 times by 2 is 8. And then we've got the other brackets, but it's at this stage we might start to want to rewrite the stuff inside the brackets as well, because we notice this 5 over x squared, and we might remember that, well, one of two ways you could view it. Either you could view it as remembering that any power that's on the bottom of a fraction could be written as that same power multiplied by -1 if you want to write it on the top of a fraction. So therefore you could rewrite this as 5 lots of x to the power of -2. Another way you could look at that is we're dividing by x to the power of -2. Because we didn't have any x's on the top, that means it's like an x to the power of 0. So you're doing x to the power of 0 minus 2, because you're doing x to the power of 0 over x squared. So that's another way of viewing what we did there. Okay, now we've got a situation very similar to the previous example. We've just got to multiply the brackets out. So that means we're going to do 81 times by, well, no numbers. Well, technically a 1. So that means 81 times by 1 is 1. 81. And then we've got x to the power of 8 times by x to the power of 3. In that scenario, we add the powers. So that's going to be x to the power of 11. Then we're going to be doing subtraction, because it's going to be a -5 times by a positive 81. 81 times by 5 is something you could type into the calculator. You'll get 405. And then, timesing the power things together, we've got x to the power of 8 times by x to the power of -2. I know that's a negative, but we're still going to add the powers. So it's 8 plus -2. And 8 plus -2 is, of course, 6. So therefore, we're going to have x to the power of positive 6. So that's that one, what that one simplifies to. Okay, but what other skills will we need to be using index laws as part of? Well, it won't always be a case of using them to combine stuff. Sometimes we wanting to separate things. So it's possible that you might sometimes end up with things like this appearing. And okay, there are, certain things we can do with algebra that looks like that, but sometimes it might be more beneficial to realize, first of all, that 2x means 2 times by x. Sorry, that wasn't meant to happen. Let's cross that out. 3 is 3 to the power of 2 times by x. But of course, multiplication doesn't matter what order you do it in. So another way of viewing this is it's 3 to the power of x times by 2. Okay, some of you are looking at me wondering, why is that useful? Well, ultimately, it gives us two options. If you had this, you could choose to write this as 3 squared to the power of x, if you wanted to. There are some scenarios where that might be something you wanted to do, because you then realize it's 9 to the power of x, and that might match up with some other things you have in an equation or something like that. But another thing you might want to do is, if we wrote it like this, that might make you view it in a different way, because instead of 3 squared to the power of x, you might now view it as 3 to the power of x all squared. And that might, again, interact with other things in your equation in a different way, depending on what else you have. So it's worth pointing out, depends what you've got in the scenario you're dealing with, you're going to have to adapt, but being able to break things up using index laws is quite important. Another example of that is we might even have, I don't know, something like 4 to the power of x plus 3. And it might be beneficial for you to realize that this could be split up as 4 to the power of x times by 4 to the power of 3. That's the reverse of that first index law we looked at the beginning, where if you multiply, you add the powers. The reason that's beneficial is because then you realize that 4 to the power of 3 is a number, which is specifically 64. So you realize this is 64 lots of 4 to the power of x. And again, that might be beneficial for you to be able to combine with other things once it's been written like this, for whatever reason. So be aware, sometimes index laws are useful to combine things, sometimes it's useful to help you split things up. Okay, there's other reasons though that index laws can help you. They can help you with specific problems like this, which is a very niche thing, because actually there's something later in Maths A-level we're going to be looking at to help us deal with equations of this type. But sometimes index laws help us solve these things a bit quicker. So the way that these work is, first of all, realizing for this very simple example, the bases that are being taken to two different powers, are basically not really having that much of an impact on the equation itself, because it's the powers that are the only thing that's different, and therefore, in order for the equation to stay true, we just need the powers to be balanced. And so therefore we can jump straight to, if I can draw the number 9 correctly, there you go, we can jump straight to saying the powers must be equal to each other in order for this equation to stay the same. That's only true though because those two bases, the two 5s, are the same as each other. But, once we've realized this, then it is just a simple case of solving this classic style equation, and therefore we get the answer x equals 11 over 7. Again, you'll notice I'm writing that as a top-heavy fraction, because 11 over 7, although we can write it as decimal, you're either going to have to round it or use recurring decimal notation, and we prefer to avoid that at A-level. Anyway, that one worked very nicely because the bases are the same, just to reiterate that. Whereas the problem is, if we have one like this, another second question, unfortunately, we don't have that to our advantage anymore. The reason that causes a problem, because if we now start trying to treat the powers as an equation equal to each other, that would be an untrue equation. Because one of the main things that makes equations work when we're trying to solve them is that we're able to do the same thing to both sides, and that doing so makes sure everything stays balanced. However, if we look at this equation, the problem is we've got a base of 3 on the left, which means that if I was to do an action to the power, like adding 1 to the power, that would be equivalent to timesing the entire left-hand side by 3. due to, adding in the index laws, the same as multiplying by that base to that power. And that's different to what happens if I look to the right-hand side and I decide to add 1 to the power of that side. If I decide to add 1 to the power of this right-hand side, I would be doing something equivalent to multiplying the entire right-hand side by 27. And the problem is, therefore, that's a different action to what I was doing on the left. So I can't make the powers equal to each other yet because the bases are different. So not a problem though, because what we can do is we can use our knowledge of indices to help us. Because you might realize that 27 is secretly 3 to the power of 3. And that means we can substitute 27 for 3 cubed in the equation. That means the equation will now become 27 has now been replaced with 3 to the power 3, so put 3 to the power 3 in brackets, because that's always a good way of doing a substitution properly. And then the the power of x plus 2 is still happening to that. So putting that there, we have this. Now we have something we can work with because we've got the brackets of something to a power to another power on the right hand side, so we can use that index law that involves multiplying the powers. However, be careful, this power is coming as a whole, so therefore all of x plus 2 is having to be multiplied by the 3, so make sure you use proper use of brackets to ensure all of that is happening. So you can see how I've written it there. That's important because that then reminds you that then if you want to simplify it further, you have to multiply out the brackets in that power. So therefore, actually, that power will become 3 times x, which is 3x, and 3 times plus 2, which is plus 6. Now the powers are the same. Now the bases are the same. We are now able to equate the powers, and that allows us to get the equation 4x equals 3x plus 6. And that's a nice, super easy equation to solve because it leads us to the answer of x equals 6. Something I would recommend with these, and in fact in general in maths it's a good idea, but particularly with these when people are a bit unfamiliar with what they are or aren't allowed to do, is take your answer and substitute it back into the original equation. Because that's always a very quick way to tell you if you've done it right, or whether you've done some sort of illegal move halfway along. Your solution to the equation should solve or work in the original equation. One more example we're going to look at, and that's basically just taking all of what we just did, but up to another level, just gathering lots of different skills we've looked at in this video all together. So, same problem, we can't create an equation based on powers because right now there's so many different things happening all at once. Just saying the powers equal to each other would not be balancing this equation. So what we've got to do is we've got to do some simplification or rewriting first. So the left-hand side, of course, we've got that index law where we've got a power to another power. So therefore, we're going to end up multiplying those two powers together. So x times by 3 could be written as 3 lots of x, 3x, in other words. And on the right-hand side, well, you've got a couple of different options. You could decide to simplify this because you could realize that it's 2 divided by 8 to the power of 2 minus x. And of course, we have something on the bottom of a fraction is the same as putting that thing on the top of a fraction, but minus 1 lots of the power we have. So therefore, this is 2 lots of 8 to the power of minus 1 lots of 2 minus x. So that's one way you could deal with this. But even then we've got a problem. We still can't equate the powers because we've got different bases, and even then we've got this extra 2 out the front of one of the things that we don't like it being there. So what we need to do is again make everything the same base. Now be careful, it's very tempting to go, oh, 8 and 16, they're linked because 8 doubled is 16, but that's multiplying, not powers. So the thing you've got to realize instead is actually all these things could be written as the powers of the same number. All of these are powers of 2 because we got obviously just the number 2, which is secretly 2 to the power of 1. We've got 8, which is secretly 2 to the power of 3. And then lastly, we've got 16, which is secretly 2 to the power of 4. So we can replace everything so it's written in terms of 2 to the power of something. So 16 is will be 2 to the power of 4 to the power of 3x. So again, make good use of brackets to make sure it's happening properly. We've got the 2, which is secretly 2 to the power of 1. And then we've got the 8, which is secretly 2 to the power of 3. But then that's being taken to minus lots of 2 to the power of minus x. And as I hadn't done anything to that power yet, other than the step I'd done in the first step, I've got to write it, in the same way with the same notation as before. Okay, now I can start to apply more index laws to simplify things further. We can do the 4 times by the 3x, using that index law to get 12x on the left-hand side as the power. On the right-hand side, well, I've got to keep the 2 to the power of 1 for the moment because I've still got to do stuff to the other thing that's inside the brackets. So first of all, I've got to deal with these brackets in the power. So therefore, I'm going to still keep the 2 to the power 3 as 2 to the power 3 and multiply the brackets in the power to get minus 2 plus x. Okay. That means now I can then do some more work because I realize I've got to keep loads of the other things the same, but it's 2 to the power 3 to the power of minus 2 plus x. That minus 2 plus x, again, is secretly all one big chunk. So therefore, when applying the index law, when I'm doing something to the power of something to the power of something else, I'm multiplying the powers, but I've got to make sure it's 2 to the power of 3, lots of, in brackets, minus 2 plus x. Okay, doing more simplification. We can now multiply out those brackets. I did tell you it would be quite a hench example. So then we've got 3 times by minus 2, which is minus 6. And we've got 3 times by plus x, which is plus 3x. Okay, we're not done yet. We still can't equate the powers because we've got more than one thing on this right-hand side. So the next thing we've got to do is we've got to use the index law where if we multiply two things together, which is what's happening here, I add the powers. So it's going to be 1 plus minus 6 plus 3x on the right-hand side. So 2 to the 12x equals 2 to the power of 1 plus minus 6 plus 3x. That simplifies to 2 to, oops, that was meant to say 2 to the power of 12x. 2 to the power of 12x equals 2 to the power of minus 5 plus 3x. And oh my goodness, finally, we've got to the point where we've got the same base, just one base, one thing on each side. So therefore, we can now finally equate the powers and then solve that equation now as it is. So doing that, you'll end up with 9x equals minus 5. And that means we'll get the final answer of x equals minus 5/9. Okay, that was a particularly horrible example, but it shows you how you can apply these laws all together while also showing you some of the things you've got to be watching out for, doing maths properly to ensure the proper actions are happening, making good use of brackets, making sure you're following things like bid maths to make sure the right things are happening in the right order, which things do you deal with first, all that sort of stuff. Okay, with that said, that will do us for today. I hope you found some of the things in this useful, and hopefully I might even see you in a future video.